Now that we can perform single and two-qubit gates and very rudimentary quantum algorithms in germanium, it's natural to ask and to consider the question like how would we scale to larger systems? Can we, for example, just scale the way we're doing now and build a larger two-dimensional system of quantum dot qubits? And there, the common vision is that this will have some limited range. In particular, if we're already looking into the interconnects, it will be very challenging to reach the middle qubits in a larger array. Simultaneously, we also will need to obtain some efficient control. If we compare to modern classical technologies, we're observing that while we may have billions of transistors on a chip, there may be just a few thousand control lines. And there's a strong reduction in the number of components used for a classical algorithm as compared to the number of control lines to operate them. And so just simply brute force scaling is probably not the way quantum computing should scale and can scale. And probably also not just in a simple two-dimensional array. So one question, of course, is still like how large can this array be built? And this is a very active question. But then a question is like how can we connect these arrays one to another in a quantum mechanical way? Ideally, we're using the same technology. Of course, we can consider hybrid technologies and doing this in various ways. And hopefully this will be working in a very convincing way. It will also require the considerations in the materials, in the fabrication design that enables to integrate and combine these different technologies. If we can already connect and integrate these systems using a technology or using the same technology, we may be one step ahead. And a particular way of doing this is called shuttling. Shuttling is something that may facilitate short-range and mid-range quantum links, perhaps long-range quantum links, but the shuttling or a quantum bus will probably have a limited extent to which quantum mechanical state can be displaced. So for a short-range quantum link, one can envision that it may increase the qubit connectivity beyond nearest neighbors. Imagine some sparse two-dimensional array where you have some two-dimensional quantum dots, but not a full 100% occupancy. So here and there are some qubits. Now by shuttling throughout, one can maybe displace a qubit to connect to another qubit which is not its nearest neighbors but somewhere else. And by doing this in a well-performed manner, one may be able to execute a quantum algorithm and get a rather decent connectivity between qubits. Still, this is on a two-dimensional array. We also may want to couple different registers. This can also, shuttling may also be used to obtain this. So therefore, shuttling is something that has been considered throughout. And shuttling of spins and charges has been demonstrated in gallium arsenide and silicon. At the same time, there's quite some challenges ahead. And also the process itself is rather challenging. First of all, already fabricating a device, because in the shuttling process, we need some gate structure that enables to displace quantum mechanical states from one place to another. And these are rather elaborated structures that just recently becomes in reach for our community. Nonetheless, spin and charge shuttling has been convincingly demonstrated. Coherent spin qubit shuttling in gallium arsenide, as well in silicon. Although something that hasn't been demonstrated is the actual shuttling through a quantum dot. So that shows that this is really something challenging, but it may have a long impact if we can do so. So one question is, can we also obtain single spin qubit shuttling through a quantum dot? And on top of that, we want to do this in germanium. So germanium, there's strong spin-orbital coupling. There are G-tensor fluctuations. So if we displace a whole spin in germanium, the G-tensor will change. In particular, if we're going to displace it to another quantum dot, the G-tensor may be totally different. So what will this do with the performance of the shuttling? And what will this do with the quantum mechanical state? So this is something that we're going to focus on. The way we're first going to explore this is in a 2x2 system. So we have one spin state that we leave idling, and then we have another state that we can shuttle. So we can shuttle it back and forth between two dots or between two other dots, or we can shuttle it perhaps around the corner. Finally, we could even envisage a triangular shuttling. And the way to do this is all in a dynamical way. So we initialize our system, allowing to do polyspin gate readout, initialization, and just by using pulses, we change exchange interaction, we change the detuning landscape to shuttle the states. So this is the general framework of operation. Then we first focus on the shuttling from quantum dot 2 to quantum dot 3 as a function of the detuning energy. So here you see some stability diagram where you're scanning through the intercrossing between the two quantum dots. And then what we're doing is that we're applying an EDSR pulse while we're changing the detuning. So as a function of a certain detuning, we apply a pulse and we continue the sequence. And you can clearly see here the two green lines at the top and at bottom corresponding to the resonance frequency, but corresponding to the resonance frequency of quantum dot 2 and quantum dot 3. So from this already we can observe that when we change the detuning, we're going from one to another quantum dot. In the middle, you see this rather green part. It's because we need to apply a strong burst to be able to drive the qubit in both states, because we're just driving with one plunger, and one plunger has a rather weak effect on the other qubit. And at this middle regime, decoherence is strong, and we see this rather blurry part. To investigate this a little bit better, what we can do is to, instead of applying a pulse while we're changing the detuning, is to apply a pi-2 pulse at the beginning, at the end, and then do this pulse. And then observe the free evolution. Because if we do the free evolution and the resonance frequency changes, we should clearly observe a change in the phase evolution. And clearly that's what we're observing. So we start in quantum dot 2, then in the beginning it's more or less constant. Then we start to see a slow change in the phase evolution, because already inside that quantum dot we're changing the G-tensor and therefore the resonance frequency. But once we're passing the anti-crossing, then suddenly we see a very sharp transition and a very strong phase evolution, corresponding to the 110 MHz of the two qubits. Now we can also here see a very sharp transition, because we can just pulse through it. Okay. So this is from quantum dot 2 to quantum dot 3. We can also do the same thing from quantum dot 3 to quantum dot 4. In this scenario, we still read out between quantum dot and quantum dot 2, but now we shuttle a spin down state of quantum dot 2 first to quantum dot 3 to 4, and then continue the experiment. In this case, we find a roughly 130 MHz difference. So each time there's an appreciable difference between it, and at the time this is more or less due to the random or at least unknown variations in the structure, the potential landscape that gives rise to different G-tensors. Okay, so at least this gives some hope that we can coherently shuttle spin qubits through quantum dots. Now I already mentioned that in germanium there's a strong spin-orbit interaction. We already saw something of it because we see this big difference in the resonance frequency between the two qubits. But there's more to it. Because since we have a difference in the G-tensor, and if we're going from one to another quantum dot, and we do this too fast, then we may not only have a change in the phase, we may also have a change in the qubit amplitude. In particular, if we start in a spin down state and shuttle fast to the other qubit, then the spin quantization axis in the other qubit may be different. And so from the spin quantization axis perspective of that qubit, we're no longer in a spin down state, but in a superposition state. So if we would rotate this qubit and look in that perspective, then suddenly the spin down state will have some certain angle. And we'll start to process around that angle. Now in the experiment, one way of observing this is already just by preparing a spin down state and do a fast shuttle to the other qubit and back. Clearly here you see if we cross the transition, we see evolution, the phase evolution, reflecting that if we start a spin down state, we go to the other dot with a different G-tensor and we start to process around. To further convince ourselves of this story, we can map out as a function of the magnetic field, do a Fourier transform and look at the frequency, and we see a clear pattern and correlation with the resonance frequency. And this is key. So no longer these oscillations are due to the frequency difference between the qubits, but they go with the absolute amplitude of the qubits. Why is that? Well, imagine that we're having the same G-tensor, but just a change in amplitude. In that scenario, if you go from one to another qubit, the only change is the difference or the change in that amplitude, and we're going to process exactly with the difference in frequency. Now, since we're also changing the spin quantization axis, then suddenly we're going to process with the Larmor precession, and that Larmor precession has an effect on where we end up as a final state. So suddenly we need to time not with the difference of the frequency, qubit frequency difference, but with the absolute frequency difference. So this is a key part to take in mind. Now, if we want to have high fidelity shuttling over a longer distance, we can start to ask the question, okay, how can we mitigate this? A naive first solution could be, well, let's just do this slower. Right? If we're going too fast, there's this adiabatic transition. Let's do a slow pulse and make it adiabatic. And in this adiabatic regime, we see already that it works, but it's rather slow. In this case, on the order of a few tenths of nanoseconds. Bear in mind that this is at a magnetic field of 250 millitesla. We also may want to do shuttling at even lower magnetic fields because the coherence is longer there. In those cases, the ramp time should be even longer. So we end up with a rather slow kind of operation. So it works, but it's slow, and slow causes decoherence, something we don't want. Then we can also do a more active control. First of all, we may just don't care and just do a lot of shuttling, and then do a final qubit pulse in the end to correct for any possible rotation throughout. That's one mitigation strategy. In this work here, we do another one, and that's doing a correction each time. In particular, we're going to time if we rotate a 2π rotation and then shuttle back. Because in that case, we can undo any possible rotations. Such a kind of mitigation requires careful optimization. A high resolution is needed, in particular, since the Larmor frequency is around gigahertz or maybe even above, so we need a timing accuracy which is much better than a nanosecond, putting high demands on the AWG. But if we do so, then we can recover rather decent results. First, let's focusing on shuttling basis states. Using this process, we're already covered for the 2π rotations. So in that regime, we can still achieve several thousands of shuttlings back and forth. You don't see any more the oscillations through the diabatic initialization because that's mitigated. That's for basis states. We can also do coherent shuttling, in particular by doing a pi on 2 at the beginning and at the end. And then, since we're picking up a final phase, what we're doing as the final operation is not a pi on 2 with the same phase, but we scan the phase throughout. And by then looking at the maximum amplitude, we can find out the Z phase rotation obtained, correct for that, and then taking care of that by, and we can focus on how often we can shuttle throughout. And for example, here is sequence that with a Ramsey type of experiment where we look at the free evolution, we get on the order of a few tenths of shuttlings. This can be extended then by including echo pulse, because we are limited by dephasing in our system. Particularly this 2π rotation takes some time. Still, it's rather fast, but it does take time. And so by applying an echo pulse, we can extend the amount of shuttlings throughout to the order of a few hundreds. We can also do this for spin qubit shuttling through quantum dots. So in this case, we're going from 2 to 3 to 4 and so forth. For spin basis states, this is again on the order of a few thousands. For Ramsey, it's on the order of a few tenths and a few hundreds when including an echo pulse. Remarkably, we see that the performance of shuttling through quantum dots is rather consistent with the shuttling between the quantum dots, or more or less it's the average of the two. Finally, we can also consider even the shuttling in a triangle, as you see here. In this case, there's no dedicated barrier gate, and therefore there's limited control in the shuttling from 4 to 2, but you can see that also scanning here, we can really directly go from the 2 qubits from one to another. Okay, so taking this into account, we can then also start to shuttle in a loop MF shuttlings between two qubits in a horizontal or vertical fashion around the corner and in a triangular fashion. We observed that for the triangular fashion, the performance is strongly degraded, yet we see a coherent evolution. So with this, we can conclude that coherent spin-qubit shuttling in germanium is possible, but careful consideration has to take account on the spin-orbit interaction, in particular the G-tensor. For example, by applying 2 pi pulses throughout to mitigate inattended rotations, or perhaps by actively or by just applying a series of shuttling and correcting for the pulse throughout, or maybe even time such that throughout the sequences a certain evolution is made from one quantum dot to another quantum dot to optimize the shuttling and perhaps combine even with qubit operations. To come back to the original vision of scaling, you see here the toolbox for semiconductor qubits. And it turns out that all of this is, at least the vision is compatible with germanium. We can have quantum mechanical links, for example, based on shuttling. We can make small systems, crossbar arrays, qubit operations in these grids, which can be coupled through shuttling in other ways. Another question could be, can we also integrate electronics? What type of electronics? What will be the size? And that to build an integrated quantum circuit for quantum computation or simulation. With this, I also want to acknowledge in particular the IGNITE group, everyone there, in particular also all the members of the Veldhorst Lab.